Alright, so estimating a population mean. When estimating a population mean, that's going to be a different type of distribution, so we're going to have to use a different table. We have to use a t distribution or a student t distribution to estimate a population mean. Alright. Some of the key concepts. The point estimate that we use for estimating a population mean, mu, is x bar. That's our parameter, our statistic, and that's the best estimate of the population mean, mu. And this comes from a sample. So it may be given to us in the problem. I know I've worked some homework problems for students where x bar is a given, but you have to know what it is. So you have to look at the data set and actually find x bar. Also, we need to make sure that the population is normally distributed or the sample size is greater than 30. Okay? So this new variable here with our t distribution is our critical t value, t sub alpha over 2. The critical t values are listed in the table after the z-score values. And we have to do something called degrees of freedom. That's where we take the total number of data items and subtract 1 from it, and there's a column we have to go down called degrees of freedom. Alright. If the distribution of a population is normal, then this distribution, t equals x bar minus mu over s divided by the square root of n, is a student t distribution for all sample sizes n. It's often referred to as just a t distribution. Okay? And then it says critical values are denoted by t sub alpha over 2. Alright. Of course, we know mu is population mean, x bar is sample mean, lowercase s is sample standard deviation, n is the number of data items, capital E is margin of error, and margin of error is found in a different way because it's a different type of distribution and a different parameter that we're looking at. We're looking at the mean. And then t sub alpha over 2 is the critical t value separating the area of alpha over 2 in the right tail of the t distribution. Alright, just like the last section, you know how we had p hat plus or minus e? That's how we set up our interval. We do the same thing here, except instead of p hat, we have x bar. That's our point estimate, x bar. So we say x bar plus or minus e. That's how you get the left endpoint of your confidence interval and the right endpoint of your confidence interval. The margin of error has a different formula whenever we're working with a t distribution. Margin of error is equal to t sub alpha over 2, that's the critical t value, times s, the sample standard deviation, divided by the square root of n. Now, I also worked a homework problem for some students yesterday, I believe it was, or day before yesterday, and I had to find s. So if the data set doesn't give you s, if it doesn't give you the sample standard deviation, then you have to find it, just like we learned in chapter 3. I'm usually going to use a calculator that I can get it pretty quick with. So I use the TI calculator when I find the standard deviation if it's not given. But and I know it's like that on some of the homework problems, so just make sure that you find the standard deviation if it's not given. If it is a problem where we are estimating the population mean. Okay. So let's look at finding a confidence interval. All right, here's an example. A common claim is that garlic lowers cholesterol levels. In a test of the effectiveness of garlic, 49 subjects were treated with doses of raw garlic, and their cholesterol levels were measured before and after treatment. The changes in their levels of LDL cholesterol have a mean of 0.4 and a standard deviation of 21.0. Use the sample statistics of n equals 49, x bar equals 0.4, and s, standard deviation, equals 21.0 to construct a 95% confidence interval estimate of the mean net change in LDL cholesterol after the garlic treatment. All right. So we have that n is 49, so that means that our degrees of freedom is going to be 49 minus 1, or 48. We'll need that when we find our critical t value. All right, x bar, that's our point estimate for the mean. That comes from the sample. That's 0.4. And s, that's our sample standard deviation, 21.0. Okay, so the first thing that we need to do, we want to figure out the margin of error. So the formula for the margin of error tells us we need to find a critical t value. So we need to go to our critical t chart. In your ebook, if you go to Appendix A, it's the one that is right after your z-score chart. Now, notice this left column here. We have our degrees of freedom, and it goes up by 1 until we get to 40. Then we go 45, and then there's 50, 60, 70. So if you have degrees of freedom around these numbers, just pick the one that it's the closest to. Okay? Now, the alpha that we find, I believe the problem said 95% confidence interval estimate. So 95% means that alpha equals 1 minus 0.95, which is 0.05. This is the area of the left and right tail, or this is the total area of the right side and left side. So if you are thinking about this in a two-tail way, right tail and a left tail, two tails, then the total area is 0.05. However, remember it's t sub alpha over 2. This is, if you think of it in a one tail, like just the right, then the area is 0.05 divided by 2. So we have to use 0.025. Now you notice the way that the table is given. The two tail and the one tail, they're right on top of each other. So if you just want to think about this like, okay, let me find the alpha, then just always use the 1 and 2 tails. But if you use alpha divided by 2, it's the 1 and 1 tail. But you get the same answer. I mean, it's the same column. So, you know, we had alpha was 0.05. That means use this column. Now, our degrees of freedom, we had 48. So the closest we can get to 48 in our table is 50. So remember, we're in the middle column, and I'm going to scroll down to 50. All right, right here. So our critical t value is 2.009. So So T sub alpha over 2, 2.009. Alright, now we need to use our margin of error formula. So the margin of error is critical t-value times sample standard deviation divided by the square root of n. So critical t-value times sample standard deviation, that was 21.0, over the square root of n. N was 49, so square root of 49 is 7. So this is 2.009, that's 21 divided by 7, so that's 3. So we get 6.027. Alright, so our margin of error is 6.027. So to construct our confidence interval, we want to say x bar plus or minus e, the margin of error. Alright, our left endpoint of our confidence interval is x bar minus e. So I can write it any way, it really doesn't matter. I'll write it using the inequality symbols. So the left one here is x bar minus e, so 0.4 minus 6.027. Let me double check all of those values. Is that what, yeah, that just seems really small. Okay. Alright. And then you say 0.4 plus 6.027. Alright. Just seems like that should be some type of typo, but we'll go with it. Alright, so that's negative 5.627 is less than mu is less than 6.427. The reason why I'm saying that just doesn't seem right is because we're talking about cholesterols, and it doesn't seem like a group would have an average. Maybe that's an average change or something, so maybe it is correct. Okay, so that was changes in their LDL, so maybe that was okay. Your book here, it used probably, looks like they used the same that they had here. You know, that's just a rounding deal, so, I mean, we still have the right answer. It's just whatever the thing tells us to round to, or use the same as the original set of data. If you don't have the original set of data, though, you could just use the same as what's presented in the problem. So, all right. So that means that we are 95% confident that the limits negative 5.6 and 6.4 actually do contain the population mean. Right. Both student t distributions and z distributions are bell-shaped. This shows a graph for a standard normal distribution, that's our z distribution, a student t distribution with n equals 12, and a student t distribution with n equals 3. Notice they're all pretty much bell-shaped. That means they're symmetric. Just like we could find, if we have the interval and we want to find what is x bar or what is the margin of error, but we have the interval, you can say the upper limit plus the lower limit divided by 2 to get the x bar, the point estimate for the mean. And you could say upper limit minus lower limit divided by 2 to get the margin of error. So exactly the same. Now if we want to find a sample size for estimating the population mean, then we use this formula. So n equals z sub alpha over 2 times sigma divided by e. So, to find the sample size for estimating a population mean, don't use the t critical score. Make sure you use a z. That's the same one that we've been using, that we used before this section. All right, so. And this formula also has population standard deviation in it. So if you don't know the population standard deviation, we need to use the range rule of thumb, which is the range divided by 4. Sometimes we may not have the population standard deviation given to us in the problem. All right, here's a problem where you're given everything and you just basically plug things in. We were told alpha was 0.05, so they found the critical z-score for that was 1.96. They plugged that in there. Times population standard deviation, right there. Divided by the margin of error squared. And so they got 96.04, which you round up to 97. All right. Now, the difference in what we're doing in the second half of this section from what we were doing at the first half of this section. In the first half, we have population standard deviation is not known. So when that is not known, then that's when we have to do a t-distribution. When you do know the population standard deviation, it goes back to a z distribution. Okay, so if we know the population standard deviation, we're going to go back to using the z chart. If we don't know the population standard deviation, then we're going to use a t distribution. All right, so our formula, if we do know the population standard deviation, the only thing that changes is how you find the margin of error. And it's not really that different. You have a critical value, so it's a critical z instead of a critical t. And instead of sigma, that's population standard deviation, you don't know that with the critical t, so you had an s, sample standard deviation. That's the only difference. Okay, the same types of terms here and here though. Alright, so let's say that we had this example. Let's work through it real quick. Shouldn't take very long. People have died in boat and aircraft accidents because an obsolete estimate of the mean weight of men was used. In recent decades, the mean weight of men has increased considerably, so we need to update our estimate of such mean so that boats, aircraft, elevators, and other such devices do not become dangerously overloaded. Thus, ergonomics. Using the weights of the men from a random sample, we obtain these statistics. N equals 40, X bar equals 172.55. Research from several other sources suggests that the population of weights of men has a standard deviation given by 26 pounds. All right. Find the best estimate of the mean weight of the population of all men. Construct a 95% confidence interval estimate. And what do the results suggest about the mean weight of 166.3 pounds that was used to determine the safe passenger capacity of water vessels in 1960? Alright, so if we want to construct confidence interval 95% confidence level, alpha equals 0.05, so z sub alpha over 2, it's going to be z sub 0.025, so that is the area to the right under the bell curve. That area to the right, we want that to be 0.025. So if we look that up in our chart, we need to go with the area 0.975, because that's 1 minus this. Alright, and that's how we find our critical z-score. So I'm going to go to the chart real quick, make sure I'm at the z-score, and I'm using the actual areas. So I'm looking for the area 0.975. Alright, 0.975 right here. 1.9 and then whatever this column is. It's going to be 6. How do I know? Because the common values are listed right here at the bottom. 95% confidence level, critical value is 1.96. Alright, so that's 1.96. So now we can figure out the margin of error. The margin of error is the critical z-score, 1.96, times the standard deviation, that's 26, over the square root of n, where n was 40. Alright, so I'll do that real quick. Alright, and so I got my margin of error as 8.05748, and it just keeps going on and on. So now I can construct a confidence interval. I'm going to have x bar minus the margin of error is less than mu is less than x bar plus the margin of error. So that's 172.55 minus 8.05748 is less than mu is less than 172.55 plus 8.05748. Alright, I'm going to round this to, I was given a mean with 2 decimals, so I'll round it to 2 decimals. I got 164.49. and 180.61. Here, that is a critical Z. And that's because we know the population standard deviation. All right. So you can see that's what they got. And so what does that imply? The actual, we're 95% confident that the actual lies between 164.49 and 180.61. Okay? So it is possible that we could use that today, but that point estimate that we had was a lot bigger than 166, or, you know, I say a lot, not that much, but it is considerably bigger in terms of weight. So you might want to be safe than sorry, better safe than sorry whenever constructing a boat or an elevator or something like that. Okay, and so for this section, this is section 7.3, the big question is, do you know the population standard deviation? If you do, then it's a z-score, and so we use the table just like we had before. Now, of course, it has to be also either normally distributed or n needs to be greater than 30 to use a z-distribution. Even if you know the standard deviation, if it's not normally distributed and it's not, the sample size is not greater than 30, then we have to use some other method. All right, and the same for the other side. If it's unknown, that just means it's a t-distribution. And so then, is it normally distributed? If so, we can use the t-distribution. If it's not, then n needs to be greater than 30. If it's not normally distributed and the set is not greater than 30, we don't have more than 30 data items, then we can't use a z-distribution or a t-distribution. Okay. Which brings us to the next section, 7.4. All right, and this section is on estimating a population standard deviation or variance. So we work with a proportion where we only use z-distributions. Then we work with estimating population means. Depends on whether we know the population standard deviation or not, whether we use a z-distribution or a t-distribution. Now we want to look at estimating a population standard deviation or variance. Well, think about finding a proportion. It's not too hard. Finding a mean. It's not too hard. Finding a standard deviation or variance. It's not too hard, but it is kind of a little more goes into that. So the same is going to apply when estimating a population standard deviation or variance. The types of tests that we have to use may seem a little strange at first. All right, we have something called a chi-square distribution, chi-square probability distribution. I usually just call it a chi-square distribution whenever we figure out the intervals are confidence intervals. This is definitely a little tougher than the other two, but it's still not too bad. One of the reasons why it's tougher than the other two is because the data set is not normal. It's not a bell shape, just a perfect bell-shaped curve where you have symmetry on both sides. All the other curves we've dealt with so far, the z-distribution and the t-distributions, they've been symmetric. So if we found an answer on one side, then the answer on the other side was just the opposite. So the critical t value or critical z values that we've been finding on the right side of 1.96, like on that last problem or one of the problems we worked earlier, and on the left side it would be negative 1.96. So that's the big difference with chi-square. It's not symmetric, so we're going to have a different critical value on the right side and on the left side. Okay. Now, for a chi-square distribution, our chi-square is equal to n minus 1 times s squared over sigma squared. You don't really have to have that right now. That's just like a test statistic. Chi-square is equal to that. We're more interested in how to find the margin of error. What formula do we use for the margin of error? Okay. Now, when finding the chi-square critical numbers, since we have to find one on the left side and on the right side, and we've never had to do that, you say, why would we even have to do that? If you think back to what we've been doing when we construct an interval, we say plus something on one side and minus something on one side. But since that critical value that we have with a t or a z distribution is symmetric, adding it to the right side or subtracting it from the left side, we don't even have to worry about a different critical value for both sides. It just works out for us. But when we have different critical values on each side, then we're going to have to find two critical values, of course. Now, the way that the table gives you the information is a little different from the two tables we've used so far for critical values. The two tables we've used so far show us a cumulative area from left to right. So we've been mainly, I guess you could say, with the z distributions, we focused on that whenever we were doing our probability problems and all that. The area is always cumulative from left to right. So remember, if you look at the top of that chart, you'd see something like this. And then, you know, wherever your z is, and it's cumulative from left to right. So you'd have this part shaded in. Well, with chi-square, the way that those values are listed, if we're looking for critical values, some value here and some value here, it's not going to be bell-shaped. So there's a good chance it will be something like this, which we don't even really have to worry about what it looks like. But so you can see that the right is not going to be the same as the left. And the way that the table gives you that information, it tells you the area to the right of the critical value. So when finding this value over here on the right side, this is my chi-square sub r value. I have to look up what is the area to the right of that so that I can get the chi-square sub r critical value. Sub r for right. Okay. When finding the one on the left, and I'm going to attempt to draw this same graph, kind of look the same. When finding this critical value on the left, that's our chi-square sub L. Look at the area to the right. The area to the right is going to be really big. Okay, so I have to use two different values in my table. I have to look for the critical number where the area to the right isn't that large, and I'm going to have to use another number which will be this area here. If you call that, say, area 1, then we're going to have to say 1 minus area 1, and that would give us this other area. Let's call it area sub 2. Now, I'm probably making this a little bit more complicated than it actually is, and you'll see why when we do it. It's not that tough. It's just that it's a little different. Okay. So let's look back here. Here's an example, and we're just going to work on first finding the critical values. So this is a sample of 22 IQ scores. Notice that 22 is less than 30. You know, if we have greater than 30, we could do a t distribution or a z distribution, depending on whether we know the standard deviation or not, the population standard deviation. But on this one, we can deal with smaller sets, which is probably more typical in the real world. Now, how many people can I get together for my trial? Maybe I can't get but 10 diabetics together. So anyway, going back to this problem. Construct the confidence interval for the population standard deviation, sigma, requires a left and right critical value of chi-square, corresponding to a confidence level of 95% and a sample size of n equals 22. So we want to find the critical values, chi-square, that correspond to a 95% level of confidence. Now, I'm going to write on this slide real quick. So for a 95% confidence level, what is alpha? We find it the same way. Okay, 1 minus 0.95. So alpha is 0.05. All right, but what did we always have to do? We always have to say alpha divided by 2 because there's two sides. There's a right side and a left side. So for this problem, that's going to be 0.025. Now, to find the critical value, I want this area right here to the right to be 0.025. So that's how I'm going to find my right chi-square critical value. The left one, I'm going to have to look up the area to the right of this. The area to the right is 1 minus 0.025 or 0.975. So I'm going to have to use the area of 0.975 in the table to get this left chi-square critical value. And you always have to do that for the left. You're always going to have to say 1 minus whatever we use to get the right one. Okay. So the chi-square distribution chart is right after the t distribution chart. Okay. So here is the chi-square distribution chart. We have the degrees of freedom over here on the left. So that concept is the same as we use for the t distribution, just say n minus 1. And then look up here, it says area to the right of the critical value. So for the problem we were just looking at, we would use this column to get your chi-square sub r, the one that has 0.025, because that was the area to the right. To get your left chi-square critical value, we would use this column, 1 minus 0.025 or 0.975. And then it would depend on our degrees of freedom for the problem. So let's look back at ours. Okay. So I believe we were told that n equals 22. Okay. And we were also told we were able to figure out alpha is 0.05. So alpha divided by 2 is 0.025. and then we figured out we would use this area to get our chi-square sub r term, and we'll use the area of 1 minus this, or 0.975, to find our chi-square sub L term. Let's go to our chart. Our degrees of freedom, if n was 22, our degrees of freedom is 21. Alright, so here's 21 right here. Now go over until you get to the column that has 0.025 at the top, and that's the one here. So your right critical chi value is 35.479. What did I say it was? 35.479. Alright. And the left critical value is going to be in this column here, the 0.975 column, because that's the area to the right of this critical value. Go down to 21. It'll be 10.283. Alright, so that's how you find the critical values for a chi-square distribution. Alright, since we are either trying to figure out a confidence interval for population variance or population standard deviation, the sample variance or the sample standard deviation, that is our best point estimate. Alright. And our notation that we use in our formulas is all basically the same, whatever you know. The only new notation we have really is our left critical chi value and our right critical chi value. Alright. Now, here's the formula that we use for population variance. N minus 1 times S squared divided by the right critical chi value. That's how we get the left endpoint of our confidence interval. To get the right endpoint, N minus 1 times sample variance divided by the left critical chi value. So to find the left endpoint, use the right critical chi value. To find the right endpoint, use the left critical chi value. Now, what do you think the difference in this formula is, just if we had to guess, and if we were estimating the standard deviation instead? What would you have to do to this to make it just sigma? Take the square root of it, right? So the formulas that you use for population standard deviation is really just the square root of the left and the square root of the right. Okay, and if I go to the next slide, you can see that's what they show. It's the same thing, just radicals. Now the hard part, I guess the more difficult part, is finding those critical values. If you can find the critical values, then you pretty much have it down pat. Okay? So that's really what you want to practice on. So let's practice on making a confidence interval. Alright, and this, I like this this example because it's going to use the values that we just found. We'll do another one where you have to find more critical values, but let's go through this. So a group of 22 subjects taking the IQ test, 95% confidence interval, that all looks the same. Here's what we are given now. The subjects had a standard deviation IQ score of 14.3. And we want to construct a confidence interval estimate of standard deviation. Okay. So we're going to use that information. We're going to use this right critical chi-value and this left critical chi-value so that we can find an interval estimate for standard deviation. Now the only new information we have is that the sample that we were looking at, it says, has a sample standard deviation of 14.3. Right? Yes. Okay. So now we want to use our formulas, and n is 22, so that's going to be the square root of if n is 22, that's going to be what? 21 times s squared, so times 14.3 squared, divided by, now since this is the left endpoint, I know that I use the right critical value, 35.479. So I'm going to punch that in the calculator to get that value. I'm going to go ahead and write down what I'm going to do after that so I can just do both calculations whenever I go to my calculator. This side is 21 times 14.3 squared. The only difference is when finding the right endpoint, use the left critical chi-value. So divided by 10.283. Okay. So I'm going to do that in my calculator. Alright, and I'm going to round, since this standard deviation was rounded to one place, I'm going to round this to one place. If I just round to one place, I get 11.0 for that one. And let me find the right endpoint. And the right here I have 20.4 if I round to one place. Alright, so let's see, check our answer real quick. Alright, and they rounded to one place just like us. 11.0 is the left endpoint, the right endpoint is 20.4. Alright, we'll come back, we'll do a couple of critical values in a second. Determining sample sizes. Procedures for finding sample sizes necessary to estimate variance are much more complex than the procedures given earlier for means and proportions. Instead of using very complicated procedures, we'll use table 7.2. I know there's a section on your homework, or part of your homework, where it says refer to the table, and if it doesn't give you a link to the table, then you're thinking, what table? If you haven't read the section or been here in class. This table is in your text. I believe that it's linked on the problems now, but it used to not be. I used to get a question about this every semester. So it's a little strange. Both of these two here are for a 95% confidence level. And the one on the left is standard deviation, the one on the right is variance. And these are both for 95%. So it depends on whether you're talking about standard deviation or variance. The two below them are for a 99% confidence level. And again, the one on the left is for standard deviation, the one on the right is for variance. Now, like it said, the actual calculation is a lot harder than it was on the previous two sections. And so the way that we read this table, if we want to be within 95% of the actual, then do we want to be our S within 1%, or our S within 5%, or our S within 20%? So, I mean, this table does give you some okay numbers, but these numbers are, you know, this is definitely not as complex as it would probably have to be if you were doing your own study. But luckily the questions on the homework are pretty easy to understand. They'll say, what does the sample size have to be for a 95% to be 95% confident that we are 40% from the actual? And so 95% confident is either here or here, and then whether we're talking about standard deviation or variance, you just go to 40%, and the answer for standard deviation is 12, the answer for variance is 57. Usually it just asks about 1. Okay, so like this one right here, estimate the standard deviation of all voltage levels in home. We want to be 95% confident that our estimate is within 20% of the true value of the population standard deviation. How large should the sample be? So we go to this table. We want it to be 95%, so you have to use either left or right. We're talking about standard deviation, so you use the one on the left, and it said we want to be within 20%. So go over, what's the sample size need to be? 48. Okay, so it's that easy. Really, it's just reading a table. Let's practice maybe one more on finding the critical chi-values, because that's usually what students have problems with the most. So let's find a critical chi-value. So let me find us one that we can do real quick. All right, let's look at number 10, chocolate chip cookies. Almost everybody likes chocolate chip cookies. Not my daughter, she doesn't like chocolate, so go figure. All right, so for this problem, if we want to construct a 90% confidence interval estimate of the standard deviation, then the toughest part really is finding what is our critical chi-values, our left value and our right value. All right, so if we have a confidence interval estimate, or we want a 90% confidence interval estimate, for 90%, alpha equals 1 minus 0.9 or 0.1. All right, we need to split that between two tails, the right tail and the left tail. So you say 0.1 divided by 2, and you get 0.05. All right, so the area to the right of the right critical value, we want to use the area of 0.05 to find this one. On the other side, on the left side, you have to say 1 minus 0.05, so we want to use an area of 0.95. to find the left critical value. Okay, so we're given the mean, we're given the standard deviation. What else do we need? The degrees of freedom. So we have a sample of 40 chips. So we're told n equals 40. That means our degrees of freedom is 39. Okay, so let's go to our table. Depending on the values in the table, we may have to round back up to 40. So our table does go to 39. So that's good. All right. So we want to use the column to find the right critical value. Uh-oh, that's t distribution. Let's go down to z distribution. And look, it doesn't have, it has 40, so we're going to have to use the one for 40. So now let's go up. Here's how I knew I was looking at the wrong one. Area to the right. That has to be at the top for chi-square. So 0.05, this column, and we need to go down to degrees of freedom what? So our right critical value is 55.758. Now to find our left critical value, we need to use the column for 0.95. All right, and go down to I'd love to go down to 39, but we have to use 40 because that's all we have. 26.509. Now to construct our interval, we're going to have the square root of n minus 1, so that's 39, times s squared. Standard deviation is 2.55 squared, over, since this is the left endpoint, I use the right critical value. Alright, and over here I'm going to have 39 times 2.55 squared divided by the left critical value, 26.509. Alright, so let me punch those in the calculator real quick. Alright, so I got 2 point, see there we're using 2 places, so I'm going to use 2 places. 1, 3, and 3.09. Okay, so that's how we find the 90% confidence interval estimate of the standard deviation for that problem.